Alrighty, guys, welcome back to College Algebra. Today we're going to pick up kind of where we left off last time. We introduced polynomials and learned a little bit about what polynomial functions are. We haven't done a whole lot of playing around with them, so I kind of want to spend a little bit of time today just playing around with polynomial functions, giving you a feel for what their graphs can look like, because they're varied. They can be all sorts of different things. And then just working a little bit some homework problems to help make sure you guys are feeling comfy. So let's get into it. I think the last thing we talked about on Tuesday was some factoring tricks. Ooh, QCam's down. So I think the nice place to pick up and start showing you examples would be some factoring problems. So this is MAC1105.007. And today is the 25th, right? Yeah. All right, so today I'm going to talk a little bit more about polynomials. And then we're going to talk about rational functions. I just want to remind you guys, I put it on the in the notes here last time. Exam 2 is, again, much closer than you might think. I know it's easy to kind of get lulled into a sense of security here at this point in the semester. But if you look kind of at the stuff we have between now and exam 2, there really ain't shit. So we've got the polynomial homework and the rational function homework that we're looking at right now. And then there's this little review of radicals and rational exponents and quiz 4. All of that stuff is the stuff that's open this week, right? Mostly just homeworks 12 and 13. The other stuff is a review and a quiz on that material. And then we're doing the review for test 2. So test 2 is going to be next week. That's a week from today. And it'll be run the same way that we ran exam 1. So you guys will sign into Zoom on your phones. I'll get you sorted into breakout rooms. I've got a slightly more efficient way of doing that now, so we won't spend as much time on that. And then we will get started on the test using honor lock on your computer. These were homeworks 12 and 13 respectively, right? Okay. So I'm going to pop open homework 12. We'll take a look at a few of these problems that let us employ some factoring tricks. If there are any particular problems that you guys wanted to see from homework 12, go ahead and let me know in the chat, and I can make a point of taking a look at those. But otherwise, I'm just going to grab a few that I think are like representative of the skills that we need to be practicing. I'm sorry, give me just one second. Hey, Bolo. Did you eat your breakfast? Okay, good. Okay. Yeah, it's strange. We're trying to get my dog used to eating outside because he's a very messy eater. But he's been eating inside all his life, so he's like silly about it. Okay. So maybe before I jump in and start solving problems, there's one last thing I wanted to show you guys. We talked about factoring tricks last time. That's where we finished. There's a theorem related to factoring. And that just says that the polynomial P of x has an x-intercept, which is also sometimes called a zero or a root at x equals r, is equivalent to P of X having X minus R as a factor. All right, and this is something you've seen, right? If you want to find all the x-intercepts or the zeros or the roots for a function, you have to factor that function. And then you take each little factor and set it equal to 0. If you take a factor that looks like x minus r and set it equal to 0, you'll get x equals r out. So I know that this is something that most of us probably know, but this is why factoring is so important, right? If you're trying to solve equations, it all comes down to this fact. Okay. So we've talked a little bit about mins and maxes. I guess we can run through one more of these. I'd like to do one with a word problem here. Yeah, this is okay. Absolute max. Okay, let's take a look at number 10 here. Try to get this a little bit out of the way. There we go. All right, I'm not going to redraw this graph. Rather than redrawing this graph, I'm just going to refer to it over here. But I'd like us to work through this together, just to make sure we're comfy with the core ideas. Number 12, number 10. We'll do this as an example. So they tell us that the graph here shows temperature readings in the sun X hours past noon. And up here we have temperature, degrees Fahrenheit, and down here we have time past noon. So, you know, you've got 1 hour, 2 hours, 3 hours, 4 hours, 5 hours after 12 noon. And this is the temperature, not like physically inside of the sun, but like out of your house, not in the shade, like in a sunny spot. They first ask us to identify the absolute max and absolute min. So remember what these are. The absolute max is the y value associated with the tallest point on the graph. And the absolute min is the y value associated with the lowest point on the graph. So the absolute max, if I'm looking at this, I would say is coming from this point right here. The x value there, it's exactly halfway between 4 and 6, so the x value there is 5. And the y value there looks like 94. So I would say the absolute max is 94 degrees, and it occurs 5 hours past noon, 5 o'clock p.m. All right, and that sort of language is important. That the absolute max is the y value, and it occurs at the x value. That sort of language is really important, and there will be problems on the test that suss out whether or not you've internalized that. So remember, if I ask you where is the absolute max, that's the x value or the input value. And if I ask you what is the absolute max, that's the y value or the output. Similarly, if we want an absolute min, we're looking for the lowest point anywhere on this graph. And that appears to be right here. Now we know that this is 0 and this is 2, so this right here must be 1, but it's a little bit tough. Oh, I can't zoom in here because we're in the print dialog. But if I want to know where is this little valley right here, it's halfway between this tick mark, which is 1, and this tick mark, which is 2. So I would say that the absolute min is, I have to see what that y value is there. So that y value also appears to be halfway between two tick marks. This is 86, this is 88. So this tick mark here is 87. This guy looks like it's halfway between 87 and 88. So I'd say it's 87.5. 87.5 degrees. And it occurs 1.5 hours past noon. Or if we want to give that as a time, that would be at 1:30 p.m. Any questions on part A here, how we're finding the absolute min and absolute max? Okay. Let's come down to part B. They ask us to identify any local minima or maxima. And they say specifically not to consider the endpoints. Of course, the endpoints would satisfy those definitions, but they just want us to ask, besides the endpoints, what local mins and local maxes do I have? So for part B, identify any local mins or maxes. I see quite a few, right? I see one here. This was a local min that was also the absolute min. This is a local max. This is a local min, and this is a local max. Remember, the bottom of a valley is always a local min, and the top of a hill is always a local max. They're easy to find. You just have to be careful with how you describe them. It's like increasing and decreasing, right? Anybody who lost points on the increasing and decreasing thing or missed a question relating to increasing and decreasing, I know you guys can tell where a graph is going uphill and where it's going downhill. It's about being able to describe it so that other people understand what you're saying. So make sure you say that the local min is, and then give the y value, and it occurs at, and then give the x value. Make sure that you're clear about the language. So I would say there's 2 local mins. That first local min is the one that happens to also be the absolute min, right? Local min of 87.5 degrees. Let's say y equals, and it occurs at x equals 1.5 hours past noon. The other local min is this guy right here. And we're forced to do some estimation. If we were looking at this in the main dialog, you would be able to blow this graph up. But since I'm looking at it in the print dialog, I can't. So I'm forced to estimate here a little bit. But it's definitely this valley right here. It's definitely between this tick mark and this tick mark. This is 3, this is 4. It's more than halfway, right? Halfway would be like right here. I'd say that's like 3/4 of the way between 3 and 4. So that's like 3:45 p.m. or we would say 3.75 hours past noon. Similarly, the y value here that's probably about halfway. Maybe a little bit more. So this is 88, 89, 90. I would say 89.5. So the next local min is y equals 89. Maybe we'll say 89.75. We'll say it's 3/4 of the way up. Again, if we could zoom in, then you would be able to see a little more clearly. And I promise any problem like this on a test, it'll be very clearly marked. And this occurs at 3.75 hours past noon. All right, so here are the 2 local mins. One of them was also our absolute min. But I want to be clear about this. It's very possible for a point to be both a local and an absolute min. Right? Similarly, it's possible to be both a local and an absolute max. We're going to see this guy up here, who was our absolute max, is also a local max. Questions on the local mins? Okay, yeah, Kendra, I will do that one next. All right, then let's look at our local maxes. There are two of these also. It's the top of those two hills. Each of those hills represents a local max. I've got one here and I've got one here. The local max here is between 2 and 3 p.m. Looks like it's a little bit closer to 3 p.m. I would say that that is 2:45. Yeah, 2.75 hours past noon. And the y value there is 91 degrees. So our first local max is y equals 91 degrees. And it occurs at x equals 2.75 hours past noon. My other local max is the absolute max over here, and that occurred at 5 hours past noon, and the y value there was 94. So this is the local max is y equals 94 degrees, and it occurred at 5 hours past noon. A word of warning. When people answer these questions on tests, often they just give the ordered pair instead of saying like min is this and occurs at this. Please don't do that. Please don't do that. If you insist on giving both coordinates because you're not sure what's being asked for, like if you're not sure they're asking for the y value or the x value, do it like I'm doing it here, right? Where you make clear that you understand that the min or max value is the y value and that the x value is the location or time. So if you're unsure how to describe a min or a max, this is the best way, right? This tells me everything I could possibly want to know. And it's nice to say that the min is this and occurs at this, but at least here you're breaking it down. You're giving me the units, you're telling me which one is x and which one is y, and listing the y value first if we're asking what is the local min is the right thing to do. If you have any uncertainty about this, if you're not sure the right way to write these things, please don't hesitate to ask, right? So are there any questions about how to communicate these local or absolute extrema? Okay. So we've got local mins, local maxes, absolute mins, absolute maxes. The last thing they ask for here is where or for which time intervals is the temperature increasing. So for what x values is the graph going uphill? Certainly here we're going uphill. And also here we're going uphill. So I'd say from whatever this time is to whatever this time is. And from whatever this time is to whatever this time is. And we can actually use these to verify the guesses that we made for the x values over here. So from, this is like 1.5 up to 2.75, right? So 1.5 up to, 2.7. All right, so we didn't need the 7.5 here. They're just calling that 2.7. So our last bit, part C. Which interval is the temperature increasing on, or on which interval is the temperature increasing? Certainly from 1.5 up to 2.7. And then what's this other one here? Or if you wanted to describe this in interval notation, this would be the open interval from 1.5 up to 2.7. And from whatever this x value is here to whatever this x value is here. So we called this like 3.75, and this is clearly 5. What are our options here? 3.7 up to 5. Okay. So my guess is here we're pretty good. 3.7, 2.7 rather than 3.75, 2.75. So the other interval here is 3.7 up to 5. Which in interval notation the open interval from 3.7 to 5. And on a test, I might ask you for the intervals of increase and decrease as an inequality like this, or as an interval like this, either one of them. If we don't specify, if we just say where is the function increasing or where is the function decreasing, you could give your answer in either format. But if it says in interval notation, we need it like this. If it says in inequality notation, we need it like this. Any questions on part C? All right. There was a problem that was requested in the chat, so let me take a look at that, number 27. I do want to talk a little bit about minimal degrees as we build up to this. Oh, use graphing to factor this. Okay. Sure. All right, let me build up to number 27. That's not a terribly challenging problem, but I think there's, well, fuck it, we can do it right now. So this theorem that I showed us before we started on our examples, this is actually going to be the key here. So let me come back to this. And I say use graphing. We'll do this and then go back. This is homework 12, number 27. To factor f of x equals 5x squared plus 11x minus 12. All right. So the factored form will look like f of x equals the lead coefficient, 5, times x minus, I'll call them R1 and R2. All right, when you factor a quadratic like this, you get stuff that looks like this, where R1 and R2 are the roots. Oh, I'm so sorry, Kendra. You said 26, and for some reason I saw 27. I'll go back to 26. So I want to make clear, this is what the factored form of a quadratic polynomial looks like. The lead coefficient is out here, and then you just have one factor for each root. Any quadratic can be written like this. Usually when we factor something like this with the AC method, the 5 would be like distributed over one of these. You'd have something like 5x minus 7 and then x minus 2. But you can pull the 5 all the way out, and this is sort of the standard way of writing the factored form. So where R1 and R2 are the roots or zeros, right? The x values of the x-intercepts. So let's take a look at the graph of this, see if we can figure out what the x-intercepts are, and then we'll just plug those in here, and right away that will give us the factored form, right? That's this thing. saying that the polynomial p of x has an x-intercept or 0 or root at some number is equivalent to saying x minus that number is a factor. So this goes both ways. If you know what the roots are and what the lead coefficient is, you can write down the factored form. Conversely, if you know the factored form, you can figure out the roots by setting each of these factors equal to 0. Here, they want us to look at this graph, tell what the roots are from the graph, and then use that to write down the factored form. So let's do it. I'll do this in Wabbit first, and then I'll do it in Desmos so we can get some perspective. They suggested a window. So here, they're suggesting that we view this thing in this window, right? Does everybody know how to interpret this? This is the x min, x max, x scale, y min, y max, y scale. So here, let me turn this on. I'll show you how to do this. I'm going to go to Window. X min says should be -4. X max says should be +4. And the x scale, they want us to leave it at 1. The y min, they want that to be -160. The y max, they want that to be +160. And the y scale, they want me to set that to 40. All right. So this is what they mean by these window settings. X min, X max, X scale, Y min, Y max, Y scale. So now if I want to get this graph, I just enter this function, I hit Y equals, and I enter this function. So that's 5x to the 2 plus 11x minus 12. And now I hit graph. All right. So can we see what the roots are? I can hit the trace button and sort of jump around on this thing and try to get a feel. So here's one of the roots. It's over here, where y is equal to 0. So look, when x is -3.06, y is a little bit above. And when x is -2.97, y is a little bit below. So what do you think that x-intercept is over there? -3, right? We can play the same game over here. This one looks like it should be 1. Here, when x is 0.9, y is 2. When x is 1.0, y is 4. So this guy looks like he's somewhere around 1. If we want to, we can look at a table. Let me see. So when x is -3, y is 0. That's one of our roots. But over here, when x is 1, y is 4. So it's not the case that 1 is one of the roots. In fact, I can't quite see what the other root is. It looks like it might not be an integer. So it's somewhere over here. Negative. Way on the graph here, trace. 3, 2. So looks like somewhere here y is negative. We're beneath the x-axis, and x is 0.76. If I take a little step over here, y becomes positive. So x is 0.85 and y is 0.98. So from the graph, I can easily see hey baby, the plumber's here. Give me 1 second.
All right, guys, sorry about that. So where were we? We are graphing this and using the graph to figure out the roots so we can figure out the factored form. One of these we were able to see really easily was -3, right? When x is -3, y is definitely 0. And we were able to verify that by looking at the table. And we thought the other one might be up here at 1, but when we checked, we see that 1 is not actually a root. So one of these guys is -3. Okay, so I'll call it R1. I'll say R1 is -3. Double check and make sure I entered this correctly. 5x squared plus 11x minus 12. Yeah. Okay. So I'm not sure what they intend here because the other root is not easy to see in this viewing window. We could play around a little bit, but let me go ahead and throw this into another graphing utility. Desmos is really nice. It's free. And this is probably some fraction whose denominator is 5. But let's... Yeah, so my guess here is, yep, 0.8, which is 4/5, I think. So from our other graphing utility, how could you have detected that in here? Let me be clear about that too, right? So in Wabbit or on your TI-84, if you wanted to see and verify that root was what it is, the same way we did here, the easiest way you could go about that, besides factoring this thing by hand, which is not hard. So if you were stuck here, you can just factor this, right, using the AC method. But if you really want to do it through the graph, and like we are here, it's not super obvious to see how. The move is to hit second and then window to change your table settings. Oh, sorry, second and window table set. You can set your start to wherever. I'll set it to 0, and then just move your delta table from 1. So instead of taking steps of size 1, move that to 0.1 to take smaller step sizes. And then when we look at our table, we'll be able to take these little smaller step sizes. And we see right here 0.80. While it might not be super obvious from the graph, it is pretty clear from the table. So the table function is your friend. If you're having a hard time seeing what's going on in the graph, 0.7, 0.8, 5. So yeah, here's the transition from this, which is negative, to this, which is positive. The other hint here is that the lead coefficient is 5, which tells me that the answer here is probably some fraction whose denominator is 5. And if you take 0.8 and write it as a fraction, this is 4/5. So the other guy here, R2, is 0.8. We'll write it like that because that's how we found it. So therefore, our factored form would be 5 times x minus -3 times x minus 0.8. And this is another one of those things where if this sort of problem were to show up on an exam, I think it would be curated a little bit better so that you could see more readily what the roots are from the graph. We're not meant to make you ponder that. That should be pretty obvious. The point here is to make sure that you know this, right? That you know the factored form will look like this. Before I move to another problem, I just want to address the more general thing here. A degree n polynomial will have at most n roots or zeros, x-intercepts, whatever you want to call them. So if you're trying to figure out what is the maximal degree or the minimal degree of a polynomial based on its graph, you can count the x-intercepts. Another fact. Hammy, no, Bubba, calm down. It's all right. So another fact here along this same line is a degree n polynomial. Degree n polynomial will always be expressible in factored form as a product of linear factors coming from the roots. Sort of.
Good.
And he's not hurting anybody, but he's woofing a lot. And what I mean by this is that just like our quadratic here can always be factored or always be expressed in factored form as like some constant times x minus the first root times x minus the second root, a degree 3 polynomial, yes, Brooke, you absolutely could use the AC method to factor this. They were trying to get you to run through this exercise of reading the roots from the graph and writing down the factored form like that. But if you were in a pinch, you absolutely could factor this using the AC method. So what I mean by this is that a degree 3 polynomial can be written as p of x equals the lead coefficient a times x minus r1, x minus r2, x minus r3, or a degree 4 polynomial can be written as p of x equals the lead coefficient times x minus r1, x minus r2, x minus r3, x minus r4. When we talk about the factored form of a polynomial in general, this is what we're talking about, right? Something like this, or something like what we saw up here, where you find the roots or the x-intercepts, and you know that each root corresponds to a factor. That was the theorem that we started the class with. The only other thing you need is the lead coefficient. And the lead coefficient is the same no matter what form you're looking at. So if you know the polynomial in standard form, the lead coefficient is the number attached to the largest power of x. That'll be the same lead coefficient in factored form. So as soon as you know the lead coefficient and all the roots, you can write down the factored form, even without going through the algebra process of factoring, which is pretty cool. All right, I'm going to do one more problem from this section, and then we're going to talk about rational functions. We wanted to see number 26, right? That was the other one we asked for in chat. So let's take a look at that. It says, let f of x be a cubic polynomial with zeros -5, 2, and 3. If the graph passes through the point 0, 15, write the factored form of f of x. So that's exactly what we're looking at here. Where was it? Here. Cubic. Who knows what cubic polynomial means? Yes. Lol, sorry about that, guys. Thank you. Because every polynomial has a constant term, it's not true that a degree 3 polynomial has 3 terms. So I see what you were thinking there, Brooke. But Mark and Kendra were both correct here. So a degree 3 polynomial is called a cubic polynomial, or a cubic polynomial is a polynomial where the largest power of x is 3. So what we need to do here is think like this, right? We're looking for something like this. This is a cubic polynomial in factored form. They told us 112, number 26. They told us a cubic polynomial has zeros, -5, 2, and 3. And then they also tell us the graph passes through the point 0, 15. And we want to find the factored form. We know that it should, I'll use the symbol f of x here. We know it should look like the lead coefficient times x minus the first root times x minus the second root times x minus the third root. And we know that the roots or zeros are these numbers up here. I call this R1, R2, and R3. So if I plug those guys in here, I'll get that f of x is a times x minus -5. And you do want to put that in parentheses because there's a negative here. Times x minus R2, that's x minus 2. Times x minus R3, that's x minus 3. We can clean this up a little bit. This is a times x plus 5, x minus 2, x minus 3 like this. All right. Now what I don't know, what they haven't told me here is the lead coefficient, a. I have no idea what this constant here is. But they did give me one other piece of information. They told me that the graph passes through the point 0, 15. This means that when x is equal to 0, f of x is equal to 15, or y is equal to 15. In other words, they've told me here that f of 0 is equal to 15. Or when we plug x equals 0, this expression should be 15. So let's go ahead and do it. If I plug in x equals 0, f of 0, I get a times 0 plus 5 times 0 minus 2 times 0 minus 3. F of 0, this thing I've been told is 15. This whole apparatus should be equal to 15. So 15 is equal to a times 5 times -2 times -3. So what do we have here? 5 times -2, that's -10, times -3 is positive 30. So this is 15 equals a times 30. And then if I divide both sides by 30, I'll get 1/2, or I'll write it like this, 15 over 30 equals a. But 15 over 30 is the same as 1/2. So my lead coefficient a is 1/2. Therefore, I can take this and plug it back in here. So the full factored form of f of x is 1/2 times x plus 5 times x minus 2 times x minus 3. There we go. So we've talked about the connection between factors and x-intercepts. We've talked about how to find the factored form of a polynomial. We've talked about end behavior and degrees, standard form, how to recognize whether something is or is not a polynomial, and you know all the factoring tricks. You guys now know just about everything anybody should know about polynomials, at least at this stage in their career. If you want to learn more about polynomials, these are fascinating fucking things. Come take pre-calculus with me next semester. In pre-calc, we learn how to divide polynomials. We learn how to study polynomial algebra, how to find remainders, all sorts of cool things. And if you really want, you can make a whole career out of studying polynomials through something called Galois theory. But I'll leave that to you if you want to look into it. The other thing we need to talk about, let's see how I'm doing on time. The other thing we need to talk about is rational functions. Good news is, from polynomials, it's not too hard a step to rational functions. Just make sure I'm not missing anything here. I would like to look at, I think, just one more little problem here. There's something here with this. Oh no, I guess we have covered all of it. Yeah, no, we're good. Okay, so let's talk about rational functions. There are a few things in there that will require you to think critically, but I want to make sure we have time to get through this material as well. So if you do get stuck or have any questions or doubts about the problems in homework number 12, please come see me in office hours. We have covered everything we need there. If you think carefully and hard about those, you will get through them, but I'd be happy to talk about them more in office hours. The other topic for this week is rational solutions. This is homework 13. As with all things in math, we need to begin with a definition. A rational function is a ratio of polynomials. So something like r of x, I'll use r for rational, r of x is p of x over q of x, where p of x and q of x are both polynomials. So in short, these are fractions made up of polynomials. Anything that you can get by dividing one polynomial by another polynomial is a rational function. And this opens the window to a lot of things. Kind of the simplest sort of rational functions you'll see like this. Stuff like 2x minus 6 over x plus 4. This is a rational function. And if you're not sure, the thing to do is to check, well, what's the top and what's the bottom? Here, the top, p of x, is 2x minus 6. This is a polynomial, right? Why is it a polynomial? Well, because the powers of x that show up here are all greater than or equal to 0. There's no variables under square roots, right? There's nothing like that. This is a polynomial of degree 1. And q of x downstairs, x plus 4, is also a polynomial of degree 1. So since the top and bottom both on their own satisfy the definition of a polynomial, this thing must be a rational function. Other examples? 1 over x. This is a rational function. It might not be super obvious, but if you think about it, the top, p of x, is the constant function 1, which does satisfy the definition of a polynomial. This is a polynomial of degree 0. And the bottom is just x, which is a polynomial of degree 1. Something that is not a rational function would be like this. This is not a rational function. Why? Well, the top here is a polynomial. That's not a problem. This is a polynomial of degree 2. But the bottom q of x, that's 1 minus the square root of x, is not a polynomial. Because square root x is x to the 1/2, is not an integer power of x. Right? So if you're wondering whether something is or is not a rational function, look at the top, look at the bottom. Are each of those things polynomials? If the answer to both of those questions is yes, then you are looking at a rational function. If the answer to either of those questions is no, then you're not looking at a rational function. And the first few problems in this homework set are precisely that. I just give you some functions and I ask you, is this or is this not a rational function? Things get more exciting here when we start to talk about the graphs of rational functions, because they have some features. They have some features that polynomial functions don't have. And we try to keep this simple, but it's worth knowing that with a little bit of patience, rational functions can be very, very complicated, very, very fascinating things. Most of the rational functions we'll show you guys in this homework set have a linear numerator, there's a degree 1 numerator, and a degree 1 denominator. Why isn't this loading? Mark asked an interesting question. So do you need the TI-83 to graph a rational function? Are there ways of kind of eyeballing it? Yes to both, right? If you want a good graph, using a graphing utility is wise. I'm going to try this again. But there are ways that you can tell what's going on with a rational function without graphing it, at least not without using a graphing utility. And those are the tools, or the techniques that we would use to graph these by hand. So there we go. Oh, this is the rational expressions one, isn't it? It's not this. We want rational functions and their graphs. Come here. Why don't you want to load? Sometimes I swear Pearson just fucks with us to fuck with us. All right, yeah, here we go. Right, so is this or is this not a rational function? Yes, this is, right? Because the top is a polynomial of degree 3. It's all positive integer powers of x. The largest one is 3. The bottom is a degree 1 polynomial, right? It isn't a polynomial because we've got only positive integer powers of x. And here it happens to be degree 1. So how do you find the domain of a rational function? Let me take one of the examples from here. To find the domain of really any function algebraically, what you should do is look out for ways you can kind of upset the function. What things can you do that would give us an expression on the right-hand side here that isn't defined? We know that polynomials, the domain of any polynomial is always all real numbers. There's nothing you can do to piss off a polynomial. So there's nothing you can do to piss off the top. And there's also nothing you can do to piss off the bottom. They're both polynomials. But you can kind of piss off the fraction as a whole. The only thing that fractions really don't like is when the bottom is 0. So to find the domain, figure out where the bottom is equal to 0, then exclude and kick out those numbers. And this is true for all rational functions. This is our first kind of, we call them domain red flags, or things you need to watch out for when you're finding the domain of a function. The bottom here would be equal to 0 if and only if x is equal to -4. So we must exclude -4 from the domain. So you guys remember that very first activity we did where I had you write down a bunch of sets in interval notation? A few of those sets were like all real numbers except for this and this. Here, our domain is all real numbers except -4. And that's -infinity to -4 unioned with -4 to positive infinity. If you're having trouble seeing it, you can draw this on the number line. It's -4. I know I want everything to the left of -4 and everything to the right of -4, but not -4 itself. So this interval here is -infinity up to -4. That's this piece. And this interval here is -4 up to positive infinity. That's this piece, and we join them with a union. And this is always true for rational functions. If you want to find the domain of any rational function, figure out where the bottom is 0, then kick those numbers out. Horizontal asymptotes are really the most exciting thing we have here. So let me show you some pictures. Let's take a look at the rational function that we were looking at just now. 2x minus 6 over x plus 4. And let's zoom way out. If we want to see what our domain is, notice what's going on here at -4. As x gets closer and closer to -4, the bottom of this expression is getting closer and closer to 0. And if you divide something by a number that's close to 0, you get a very big number. So as x gets closer and closer to 4, the y values here are blowing up. This is called a vertical asymptote, and it happens on both sides. Sometimes it'll look like this. Sometimes it'll look like this, where it goes up or down on both sides. These come from places where the bottom is 0, right? So the vertical asymptotes, you find those at the same time you find the domain. Vertical asymptotes will be solutions to the bottom equals 0. It's a vertical line, so we'd write it as x equals some constant, and it comes from setting the bottom equal to 0. The other kind of interesting behavior that's going on here is as we wander further and further off to the right, it's not like a polynomial where the polynomials just end up going up. Either they go up on one side and down on the other, they go up on both sides, where the function blows up. Here, the function seems to be like getting closer and closer and closer to some particular number as we run off further and further to the right. You guys see this? As I go further and further and further to the right, this function isn't going up. It's not running off to infinity. It's like getting closer and closer to 2. Yeah, 1.8, 1.9, 1.97. If we zoom way out, it starts to look like a horizontal line. So all the fun, crazy stuff is going on over here. And the other kind of interesting thing that's going on is that as you go further and further to the left or to the right, the function approaches this blue line, which is the line y equals 2. So these are called vertical asymptotes, and these are called horizontal asymptotes. I'm going to show you how to find them. All right. So let me put some stuff in boxes here. We can kind of keep track of what's important and what you need to remember for later problems. To find the domain, set the bottom equal to 0, and then exclude those numbers. To find vertical asymptotes, just take the numbers you excluded from the domain. And write x equals those numbers. So for example, the function that we're looking at here, we found that the domain was all real numbers except for x equals -4. So here, our vertical asymptotes, there's just one of them. Here, our vertical asymptote is just the vertical line x equals -4. And it will always be x equals a constant. And the other kind of interesting things we want to be able to find here are the horizontal asymptotes. Those are pretty cool. To find horizontal asymptotes, there's a rule. There's 3 cases. If the degree of the top is bigger than the degree of the bottom, there is no horizontal asymptote. All right, so that part is simple enough. If the top is like a quadratic and the bottom is a linear, then that rational function has no horizontal asymptote. If the degree of the top is strictly less than the degree of the bottom, then y equals 0 is the horizontal asymptote. All right, so if the top is linear and the bottom is quadratic, then y equals 0 is automatically going to be the horizontal asymptote. What about in this case, like the function we're looking at here, where the degree of the top is 1 and the degree of the bottom is 1? In this case, we saw that y equals 2 was the horizontal asymptote, right? This function, as we zoom way out, the red gets closer and closer to the line y equals 2. Where do you think that 2 is coming from? Any thoughts kind of where in this expression the y equals 2 that we're seeing here is coming from? Yeah, exactly, Logan. Yeah, it's the lead coefficient of the top. Now watch this. If I change the bottom to have a lead coefficient of 2, I can do that like this. That moves my horizontal asymptote down to 1. So what really is going on here, I'll put it back, is we're taking the ratio of lead coefficients. But you're exactly right, it's coming from the coefficients. So the last case here is the interesting one. If the degree of the top is equal to the degree of the bottom, then the line y equals, there's no nice way to write this, the ratio of lead coefficients is the horizontal asymptote. So this is what we call the 3-case rule for finding horizontal asymptotes. And I fully acknowledge that it's a little bit complicated, but once you practice with it, it will start to make sense. So for our function, for r of x equals 2x minus 6 over x plus 4, we have to figure out first which of these 3 cases we're in. So the degree of the top is 1, right? It's a linear function. The degree of the bottom, that's also a linear function. The largest power of x there is x to the 1, so that's also 1. So since these match, the horizontal asymptote must be y equals the ratio of lead coefficients. So what do we mean by ratio? We mean the fraction formed out of the lead coefficients. So the lead coefficient upstairs is 2, and the lead coefficient downstairs, the coefficient of x here, is 1. So that's just y equals 2, and that's how I found that. So let's look at a few more examples where we're finding these things. Other stuff that you will want to find for rational functions is x-intercepts and y-intercepts. So before I move to another example, let me just share with you really quickly how to find these. To find x-intercepts, for a rational function, set the top equal to 0 and solve for x. So for the rational function we were playing with here, our numerator was 2x minus 6. So if we set 2x minus 6 equal to 0, we can add the 6 to both sides and get 2x equals 6. And then we can divide both sides by 2 and we get x equals 3. So there's only one x-intercept for this guy, and it's x equals 3. And if you look at the graph right here, that's your x-intercept, right? And that's the only one. To find y-intercepts, there's really only ever one y-intercept. Plug in x equals 0. And that's really the full list of things that we would want to do with rational functions. All right, these are all the things that we need to be able to find. So I'm going to scroll through these. Give me just 1 second here. I'm going to back up to the top. So to find the domain, set the bottom equal to 0. Then exclude those numbers. To find vertical asymptotes, take the numbers that you had to exclude from the domain. Those will be your VAs. Just write it as x equals. That's the equation of the line. Right? Remember, a vertical line is always x equals a constant. A horizontal line is always y equals a constant. A vertical line, and these vertical asymptotes are vertical lines, will always be x equals some number. Take the numbers that you had to kick out from the domain, and x equals those will be your vertical asymptotes. To find horizontal asymptotes, we follow this 3-case rule. This is maybe the most complicated piece here. So it all depends on the degree of the top compared to the degree of the bottom. If the degree of the top is bigger than the degree of the bottom, there's no HA. If the degree of the top is smaller than the degree of the bottom, then the horizontal asymptote is automatically y equals 0. If the degree of the top is equal to the degree of the bottom, then y is equal to the ratio of lead coefficients, will be your horizontal asymptote. X-intercepts and y-intercepts come pretty naturally. X-intercepts come from setting the top equal to 0, which is equivalent to setting the whole thing equal to 0. And y-intercept, as always, comes from just plugging in x equals 0. A little note here before we move on. Y equals a constant is always a horizontal line. So your horizontal asymptotes should always look like y equals some constant, and x equals a constant is always a vertical line. So your vertical asymptotes should always look like x equals some constant. We always want the equation of the line. Don't just tell me the vertical asymptote is 2. Don't just tell me the horizontal asymptote is 7. You got to tell me y equals 2 or x equals 7. All right, so your HAs should always look like y equals a constant. And your VAs, vertical asymptotes, should look like x equals a constant. It's not that I won't know what you're saying, it's just good communication. And I'll tell you right now, there are problems on the test and indeed on the department final that will check for this sort of thing. So make sure you get it straight. Make sure you know what vertical lines and horizontal lines look like algebraically. Okay, let's look at 1 or 2 more examples. I'll take them from your homework. Oh, we are just about out of time. Okay. I think you got everything you need. Yeah, these aren't too bad. All right, I am going to have to end it here because we're out of time. You do have everything you need to go through this homework. There's really nothing besides what we just ran through here. I know that we haven't seen lots and lots of examples. So next Tuesday, I will do a few more examples of problems with rational functions like these. I invite you guys to play around with graphing utilities like Desmos in addition to getting to know your TI-84. But you know, if you graph something in Desmos, take the time to graph it in your TI-84 or 83 also. Before I let you go, let me go ahead and show you what this would look like here. You need to use parentheses, especially in the TI-83 when you enter these. So this would be like parentheses 2x minus 6, close parentheses, divided by parentheses x plus 4. super duper important that you put the top and the bottom in parentheses. My window settings, let me set these back. These were something funny from the previous problems. Let's go to -10, 10, 1, -10, 10, 1, and hit graph. And you see we get the same picture. It's kind of zoomed in on this part of the graph. So if you want to see more, we can back things out. -20 to 20, -20 to 20. And that'll get us a slightly better picture. Some calculators will draw the vertical asymptote in as though it's a part of the graph. It is not a part of the graph. I want to make that real clear. Some calculators, like I think the TI-83 does this, and maybe the non-plus version of the 84, will have the vertical line that is the vertical asymptote drawn in right here. Please don't include that when you sketch the graph yourself. That is not a part of the graph. If you're going to draw them in, and you should draw them in as dotted lines or dashed lines like I've done here, and label them. All right. How did I enter it? So I put the top in parentheses, and then I hit the divide button, and then I put the bottom all in parentheses. That's the trick, right? So when you type these functions in, rational functions, or any expression with fractions in a calculator, you always put the top and bottom of the fraction in parentheses. Alrighty, I'm going to go ahead and end it here, guys. If you want to see more problems today, you can come see me in office hours. I'll have an office hour starting in about 10 minutes. Otherwise, we will work a few more of these next Tuesday. But then on Thursday of next week, we're going to have our second test. It's true you can play around with the zoom function in the calculator. I recommend using the window settings because you can get a little bit lost in the zoom menu. It can be a bit confusing. But there are other functions on the calculator that will help you adjust window settings. I think manually adjusting the window settings is the way to go, though. That way you'll be understanding what you're looking at versus clicking zoom and then not knowing what your scales are. But Kendra reminded me, and we can share it with you guys, that you can also learn how to use the zoom function on your calculator. There is a calculator workshop, a TI-8384 workshop run by the Learning Commons. If you're curious about that, talk to some of the tutors over there, or Larry Warren at the Learning Commons. He should be able to hook you up with whatever the most recent or newest date is for that TI-8384 workshop. All right, take care, guys. And if you want to see more problems, come see me in office hours today. Otherwise, I'll see you all next Tuesday as we prep for the test, which is next Thursday.